The idea of just chemicals disappearing over time in a measurable way and being able to describe that with how they collide, hopefully, is pretty straightforward and maybe familiar from a previous chemistry class. The way we turn that into a quantifiable measurement of reaction that allows us to make some predictions is likely new. That idea of turning it into an equation and looking at the quantities is called a rate law. Collision theory is an explanation. A rate law is a mathematical statement. Rate laws are based upon experimental evidence. The coefficients in the equation do not tell us the rate law. The collision theory does not tell us the rate law, although we'll see some coincidental connections and some connections when we get into more detail. But the rate law gives us an idea of, based upon initial conditions, how fast will the reaction go. So all rate laws, no matter how we determine them experimentally, and we'll see two main methods and other theoretical methods, look like this. The rate of reaction is proportional to the concentration of one reactant raised to a certain power and the concentration of the next reactant raised to a power and sometimes even more. The powers we are raising it to are called the reaction order. We'll see right down here, that basically is telling us how much does the concentration of A impact the rate of reaction? How much does concentration of reactant B impact the rate? It's very tempting to think of these based upon coefficients, but these numbers, no numbers in our rate law are based upon the coefficient from the overall reaction. The rate constant we'll explore even more later, but it's a proportionality constant. It takes these concentrations and allows us to know the rate. The value of the rate constant depends on the temperature. If it gets hotter, we can understand that, well, if I'm not changing my concentrations, but it's going faster, it's because my K would be going up. So K does account for temperature. It also connects to the other factors we looked at in collision theory as they connect to rate. So here, as we look at reaction order, those X and those Y are the exponents of how much the concentration of that thing matters. If we raised our concentration to a value or an exponent of 0, we call that a zero order reaction. That means that the reaction rate does not depend upon the concentration of that. So if reactant A is raised to the 0 power, it doesn't matter if I put in more chemical or I don't put in more chemical. That's not going to make it go faster. It keeps going at the same rate. Although that seems to contradict the collision theory we just looked at, as we get into more detail later, we'll see why that works. But a zero order reaction in terms of concentration versus time would just be a straight line. The amount is going away and nothing is speeding up or slowing down how fast that is going away. First order sometimes seems to make the most sense, although 0, first, and second are all very common. First order is saying that the rate of reaction is proportional to how much I have here. It directly connects to our simple understanding of collision theory, and we'll see it is supported even later. But as my A goes away, the reaction is slowing down. There's not as much of chemical A to collide, and therefore the collision isn't happening as fast. It's directly proportional. It slows down as that goes away. A second order reaction, and we can have third, fourth, or fifth order, although those become much more rare. Second order is saying that the rate is proportional to the square of the concentration. So that's an even curvier curve, but that's saying as I use up my A, as that concentration drops, not only does it slow down, but it slows down exponentially. So there are some reactions based upon the way the chemicals are used and the way they collide, try to put those words together, that a concentration of a certain chemical is that important. As it goes away, it is consumed such that the reaction slows down based on the square of that concentration. So I said before, but to say it again, these are not based upon coefficients. These are based upon experimental evidence. So in the next few videos and problem sets, we'll look at what does that experimental evidence actually look like, or how can I determine my reaction order.